Okay, so we're in 10.3 now, and we're going to spend 10.3 and 10.4 talking about this topic, which is polar coordinates. 10.3, the focus is just on the basics of polar coordinates, what they are, and kind of how to interpret them, how to plot points in polar coordinates, how to convert back and forth between what we call Cartesian coordinates and polar coordinates. The next section, 10.4, we're going to be focusing on graphing specifically with polar coordinates. So to begin with, let's discuss the polar coordinate system. Since all the way back to your pre-algebra days, you've been taught how to plot points in the coordinate plane. Points have an x and a y coordinate, which you interpret as basically the distances between that point and these horizontal and vertical axes. The x coordinate represents the, you could think of it as the base of this triangle even. The y coordinate would represent the height of this triangle to get from the origin to that point. If I were to draw another right triangle right here, you'd see that this creates a rectangle with one corner of that rectangle being the origin and the opposite corner being the point xy. For that reason, sometimes our coordinate system, where we use x's and y's, we sometimes call that the rectangular coordinate system. It's also called the Cartesian coordinate system. That's named after a mathematician. You'll see me use both of those those terms. So that is far from the only coordinate system that's worth considering in math. And what we're talking about here is polar coordinates, which assigns different meaning between this first and second coordinate in a point. So rather than think of the coordinates of this point as the horizontal and vertical distances from the origin, instead we're going to think of them as r, which represents the actual distance between this point and the origin. That would be the length of this blue line right here. And then theta is going to represent the angle that this line segment makes with the positive x-axis. Notice that's another way of interpreting the position of that point, its distance from the origin and the angle that this creates. So what we're going to do is just start getting familiar with working with polar coordinates, plotting them, and then going back and forth between the rectangular coordinate system and what we call the polar coordinate system. So let's start with this down here. What I'm looking at here is called a polar grid. And the reason we like polar grids, basically what you're looking at is the coordinate plane. So this coordinate plane, the origin here is appearing right here. And we've superimposed several concentric circles centered at the origin. We interpret these circles to have a radius of 1 for the innermost circle, then 2, then 3, then 4, and then just kind of counting out in that fashion. If we want to count by different values, there'll be numbers indicating what these represent. But notice that any point on this circle here is going to have a distance of 1 from the origin. This circle is going to consist of all the points that are a distance of 2 from the origin. That's easier to graph points in polar coordinates if we have these concentric circles than it is if we just use this. This way of representing the coordinate plane is better suited for rectangular coordinates, x's and y's. So not only that, through the origin here, we have lines which you can kind of think of as like the spokes in a wheel. And these lines are there to indicate what the angle against the positive x-axis would be. So I used a polar grid generator. This is a polar grid to create this. I determined, how many circles I wanted and what the angles should be and all that kind of stuff. You can kind of search around for those if you want, or if you just search polar grid paper on Google or something, you can find pages of this that you can just download and print. Or you could draw them freehand. It's easier to work with a printed version. But what I want to do here is take these 3 points, these 3 ordered pairs, and plot them in this polar grid. So to start with, this is the point 2, 3 pi over 4. This is not an x and a y. This is an r and a theta. I'm using this, which is the polar coordinates corresponding to this point. So the 2 here means that I'm going to plot my point 2 units away from the origin. I keep calling this the origin, but I should point this out as well. In polar coordinates, we don't call this the origin anymore. We call it the pole, P-O-L-E. So I'm looking for a point that's 2 units away from the pole. That would mean that the point that I want to plot here would be somewhere on this second concentric circle. And then the 3 pi over 4 tells me that the angle that this point creates with the positive x-axis should be 3 pi over 4. So I'm going to go 1, 2, because this is the spoke corresponding to 3 pi over 4, and I would plot that point right there. That's the point 2, 3 pi over 4. It's kind of difficult to see that, but that's the point that we're talking about there. Okay? Next up, we have this point in polar coordinates, negative 3 pi over 2. Now, initially, it may seem like this doesn't make any sense because r, which again is the first coordinate that we read in polar coordinates, is supposed to represent the distance from the origin or the pole. However, the distance we usually say can't be negative, so this may initially seem like it doesn't make any sense to have a negative 3 here. However, we do have an interpretation for this in polar coordinates. So what I'm actually going to do is start with the angle pi over 2, which is here, and I'm going to find where 3 pi over 2 would be. So 1, 2, 3. Here's the third concentric circle in the direction of pi over 2. Now to get negative 3 pi over 2, what I want to do is reflect this point, or you could also think of rotating it 180 degrees so that it points in the opposite direction. That would actually move it down to 3 pi over 2. So this is the point negative 3 pi over 2. So again, when you're dealing with negatives, the angle here is not going to appear to match the angle that we're actually using for that point. And that's because we start with this angle, pi over 2, but then reflect it to a new position. Finally, this point I want to plot 0, 31 pi over 29. You notice the angle here is a bizarre one. It turns out that's not going to matter. So r in this case is 0. That means we're 0 units away from the pole, which means this point belongs at the pole. 0, 31 pi over 29. Now, the idea here is that the angle in this point could have been anything. As long as r is equal to 0, we're always talking about the exact same point. Okay? So there's a couple of things worth noticing with this example. And first of all, that's that a single point in the plane can be described in multiple different ways in polar coordinates. The Cartesian coordinate system doesn't have that. The point 3, 4, for example, in rectangular coordinates can only be represented by the ordered pair 3, 4. Any other ordered pair would be describing a different point. In polar coordinates, we have several, in fact infinitely many, different ways of describing any one of these points or any other point that I could plot in this polar grid. In the next example, we're going to look at how to come up with different representations for certain points. But what I want to do before I do that is talk some terminology. So in Cartesian coordinates and in polar coordinates, we have certain terms for things like our axes and the origin, the point 0, 0. The terminology changes if we go from Cartesian coordinates to polar coordinates. So in Cartesian coordinates, for example, the positive x-axis is simply that. We call it the positive x-axis. That's this part of the x-axis. In polar coordinates, we refer to that as the polar axis. So when I was going through this example down here where I was plotting these points, I used the terms, you know, x-axis, y-axis, stuff like that. But from here forward, when I'm in polar coordinates, I'm going to be calling the positive x-axis the polar axis. That's the axis that we measure theta against. The y-axis, for reasons that will become more clear when we get into 10.4, is called the line theta equals pi over 2. Okay, we'll look at graphs of polar functions and we'll see that constant functions, theta equals a constant, always looks like a line through the origin. The y-axis is a line through the origin and it corresponds to the angle pi over 2, which is why we call it that. And then finally we mentioned this one, the origin in Cartesian coordinates we refer to as the pole in polar coordinates. So these are just alternative terms that we use depending on which coordinate system we're working in. All right, let's go on to the next example here. All right. So I have a point here in polar coordinates. It's 5 pi over 4. And we want to represent this in two different ways. So one way I know that I can represent it is I can use an angle that's coterminal to 5 pi over 4. So for example, if I added 2 pi to this angle, and I called this 13 pi over 4, okay, I know that 13 pi over 4 is coterminal to 5 pi over 4. So we would be talking about the same point if I were asked to graph it. Again, 5 pi over 4, that would be down here, and 5 units away would be 1, 2, 3, 4, 5, it'd be here. But if I changed the angle from 5 pi over 4 to 13 pi over 4, that's just like rotating around one time, or making one full revolution and coming back to that same point. So that would be the exact same point, just described with a different angle. I could do that again to get my second representation. I could just add another 2 pi to this, or even subtract 2 pi, or some multiple of 2 pi from 5 pi over 4. But I want to try a different approach. Another angle that would, or another representation that I could use is negative 5 pi over 4. And in this case, pi over 4 is not coterminal to 5 pi over 4, but it is pi radians away from this, or 180 degrees away. So if I were to plot this point, I'd look for pi over 4, which is here, go 5 units out, 1, 2, 3, 4, 5. And then because I had a negative 5 for r, I would have to reflect that, taking me back to the point that we were working with in the first place. And you should be able to see there's no end to the number of possibilities I could come up with. And most of those are going to come from changing this angle, but I could derive those pretty easily. So again, I just wanted to point out that the polar coordinate system is very different from the rectangular coordinate system, and this is one of the ways where it just behaves differently. Any point in polar coordinates has an infinite number of representations, not true in rectangular coordinates. Okay, so I think in the next video we'll talk about these conversion formulas.